So as I indicated, we will be doing functional optimization in this lecture. However, let's look at basically a couple of numerical problems so that we do not forget how this constraint optimization works. And taking the derivatives and things like that will help, right? So I'm going to first state the problem, basically something like this function minimization of x1 x2 plus x2 x3 plus x3 x1 subject to x1 plus x2 plus x3 is equal to 3, right? So x1 plus x2 plus x3, it's difficult to imagine, but basically it's going to be a plane in this three-dimensional space, and then on that we are trying to minimize, right? Does it exist? And all those questions come into picture. But I'm going to basically bet that whenever you have something so symmetric in all these things, the answer is going to be, if at all the answer is there, then basically all of them are going to be equal. So x1 is x1, x2, x3, all of them will have to be equal to 1, and the answer is going to be 3 as far as the minimum value is concerned. And if you can see, basically something like we can choose x1 to be 0, x2 to be 0.5, and x3 to be 2.5 so that it satisfies the constraint. And you can convince yourself basically 2.5 into 0.5 is 1.25, which is more than less than this value. So we will see what happens, right? So what is the Lagrangian? So Lagrangian, we have a single constraint here. So x here is a vector, essentially x1 x2 plus x2 x3 plus x3 x1, that's your f of x, plus this is your g of x, is basically x1 plus x2 plus x3 minus 3 and times lambda, right? So that's your Lagrangian, and you need to set the first derivative to 0. And like I said, if you take first derivative with respect to lambda, then you'll get back the constraint, but we typically go for the other side of things, with respect to x, and see what happens. If you take with respect to x1, I'm going to get x2 plus x3, okay, plus lambda, and partial with respect to x2 is going to give me x1 plus x3 plus lambda, and partial with respect to x3 will also give me something similar. I'll get x1 plus x2 plus lambda, right? So now remember, x1 plus x2 plus x3 is 1. So therefore, substituting that in this particular thing, I'm going to get lambda plus 3 minus x1, and this one is going to be lambda plus 3 minus x2, and it's going to be equal to lambda plus x3 minus x3, right? So in other words, x1 is equal to x2 is equal to x3 is equal to lambda plus 3, okay? But if all of them are equal, and then the summation is equal to 3, so this has to be equal to 1, so lambda is equal to minus 2, right? Now, this is equality constraint, so no problem. So we get this nice point where all of them have the same value, and some lambda is typically unimportant for us. But let's go back to the original problem. Basically, can we find better than this, right? So like I said, perhaps x1 and x2 are 0, and x3 in that particular case becomes 3, and you will see basically in that particular case the value of this particular function is 0, right? And which is definitely better than the case that we have. If all x1, x2, x3 are 1, it will give you 3 here, right? So and you can find many solutions which gives you better answer than the answer that we get is 3, right? So for the particular extremal solution, I would call it, is f of this thing. Of course, g of 1 comma 1 comma 1 is 0. There is no doubt about that. So the function value itself is 3. So what is happening? Well, perhaps this is not the minimum, but it's actually the maximum, right? And that we can only check by looking at the second order condition, and one can actually take a look at the second order condition, and the second order condition will actually end up giving, unfortunately, 0. Sorry, it's not quite true. Do this. So I'll get 0 1 1 1 0 1 and 1 1 0, and I know that this is not going to be non-negative definite for any value of this thing, let alone on the tangent plane. Why is that? The trace is 0, so that means summation of all the eigenvalues is 0. But on the other hand, this is a symmetric matrix, so all the eigenvalues are going to be real. So if the trace is 0 and all the eigenvalues are real, that means at least one of them has to be negative, and therefore that will produce this thing. But on the specific tangent plane, which basically corresponds to this being 0, the gradient being 0, and then we can check, and then basically you will you will see that basically it's not going to be satisfied, right? So unfortunately this particular problem does not give you maximum, okay, sorry, minimum, okay. So let's take a look at another example, x, y, z. Again, we are trying to maximize in this particular case. So we'll see. I mean, maximization or minimization does not really matter in most of the cases unless we try to look at the second order conditions and things like that, okay. And that's the constraint. So Lagrangian is basically going to be xyz plus lambda times xy plus yz plus xz minus c by 2. So partial of L with respect to x is basically going to be equal to yz plus lambda times y plus z, right? And then you'll have things like zx plus lambda times x plus z, and then finally xy plus lambda times x plus y, okay. So how do we solve this? All these things have to be equal to 0. We need to set them to 0. So when you add all these things, basically we're going to get this adds to c by 2 plus lambda times 2 times x plus y plus z, and that's going to be equal to 0, right? Again, one can slowly see that the answer has to be symmetric, and then basically you can jump and then pick x equals y equals z, and then you'll get some value and basically go back and substitute, right, in the constraint. So if you have x equals y equals z, then basically you'll essentially get 3x square is equal to c by 2, and therefore x is square root of c by 6 and things like that, right? And perhaps that's the maximum and things like that by checking the second order condition. So hopefully you get some idea in terms of how one can use this Lagrange multiplier problem, and it can be quite painful, and we'll see how these things can be quite useful in some of the more interesting problems related to control, and then we'll see that at a later point, right? So that will bring us to functional optimization. Okay, and I don't really have any results mentioned here. We will take a look at a couple of motivational examples. More than that, most of it is handwritten notes today. So let's actually get to some interesting examples, right? So this is apparently coming from I don't know, Bible or one of the classical literature from the West. There was a queen called Dido. She was essentially thrown out of her kingdom, and then she was searching for a space, and then I believe she was probably from Ethiopia, and then she went to some nearby places, and the other place was on the ocean, and the local king there basically was kind enough, said, okay, you stick to the area where you're settled currently. On one side you have the ocean, and the other side you can occupy as much a space which will so we have, let's say, this is the ocean, and what the king said is basically you skin a cow or something like that, and then make into a strips that looks like basically long thread kind of a thing, and then basically, and that thread can be placed as a boundary on the other side other than the ocean, and then it's up to you in terms of how you're going to shape that, right? So this is the problem of Queen Dido, it's called, and she was a smart lady. I don't know what solution she provided, but she probably didn't think that we can actually go into nano level strips and then get pretty much infinity in terms of the area, right? So let's see. This problem is closely related to another classical problem that we are all familiar with, which is given a perimeter, given a say thread of length L, what's the maximum area that it can enclose? So I have a thread that is something like this, and I can probably put it in such a way that the end and starting point is the same. The length of this particular thing is L, right? So, and what is the maximum area that you can achieve? Which shape of this particular string will give you maximum area, right? Now this is called functional optimization, because after all, you're looking for a function, not some values of particular points and things like that. In the scalar case, scalar optimization case, you're looking for one x, whose value will increase the value of f of x, and then that's a single point or multiple points and things like that, but they're points in the real line. The vector case is basically still a bunch of numbers. You're looking at a vector of numbers, and which vector solves the problem. Whereas in this particular case, we are looking for function as a variable. So it x belongs to f, but that f is now full of functions, right? So we are trying to find the best possible function within this thing. So how do we define this function? In the case of this particular problem, perhaps we can put some point there and then associate a coordinate system with this, and then multiple ways of doing this. I'm going to pick polar coordinates. Essentially, for a given theta, I'm going to define my radius r theta, and essentially I'm going to find this function r as a function of theta. What should be the function r as a function of theta from 0 to 360 degrees or pi radians, and that will maximize the area, subject to the constraint that the perimeter is equal to L, right? So this is the problem. So this is a functional optimization problem. For example, the shape we have is one of those functions, right? On the other hand, I could have actually defined a rectangle, right? And then that's also a function, at theta equals 0, it is some length, and at theta this thing, the radius is going to keep on increasing till this particular point, and it starts decreasing and so on. It may be a discontinuous, non-smooth function, but a perfectly continuous function and things like that. So you can have any such functions, and among all those functions we need to find the best one. And what is the objective function here? We'll get there, right? We'll get to that in a second in terms of formulation of this particular problem. So so back when I was a student, basically I had an entire course on this particular subject, and we had a professor that showed a wonderful proof of this particular thing that does not really involve maths but then visualization, right? So what he said is, okay, so I'm going to place this particular string in some amoeba shape, let's say, and wherever you see this thing that is going inside, let's call that as a non-convex or concave shape, basically, and then reverse it, right? Reverse it, it's not exactly reverse. I wish I had technology reversing exactly there. So what I did is now, and I'm going to erase this part. Let me actually erase it. No, let me not do that. So what I did is, basically, when I flipped, I increased the area, right? I increased the area, but then the length did not change because I just flipped, right? So, and wherever you see that, you can repeat the process, right? And then the new shape also, again, it may actually create something that looks convex and things like that. Sorry, concave, right? So, and you can keep doing this, and then every step it will increase and things like that. And at what stage does it stop? Well, let's say by a miracle you'll get something like this. Is this enough? I mean, in fact, knowing that we discussed convexity just last lecture, it's clear that the final answer is going to be convex, right? So let's look at convex shapes like rectangle. Now, does this can we not basically increase the area of this? Well, suppose you do this and then flip. You cannot flip. Inside it will reduce. So what can we do, right? So interestingly, you take this and basically cut like this, right? And flip it, right? When you flip it, you're going to get something like this, right? And sorry, let's do this again. So if I do something like this, basically when I flip it, I'm going to get I'm going to let me use this different color. I'm going to get something like this, right? So again, you will get this non-convex type of shape, and then you can keep on increasing, and you will again end up with some other convex shape. So in fact, it requires a little bit of work, but otherwise, basically, even if you have things like ellipse, you can show this kind of, there is some cut when you actually reverse this in a slightly different way, you will get non-convex shapes, and the only shape that does not have that property is circle. So, Professor Michael Loss of Georgia Tech, when he was teaching our course, basically showed this proof, and I was so impressed by that, and basically I fell in love with that particular course, and then he has been wonderful after that proof also, but he went into mathematics, right? So how do we formulate it? Well, let's go back to our amoeba shape and then associate some coordinate system, and I can basically try to solve this in two different ways. First, imagine basically bunch of strips of this sectors are created, right? And each sector I'm going to basically assume some kind of straight line there, right? So in other words, my assumption here is basically I'm going to create a polygon, right, or a irregular polygon, and that becomes a now vector optimization, because we are looking at bunch of points let's say n points, n coordinates of each of these points, and then basically solve it as if we are solving the constraint problem that we saw last class, right? And that's a good method. There is nothing wrong with it, except basically if you actually attempt to solve this particular problem using that method, you will end up nowhere, and it's quite complicated if you actually stick to the rigor of that particular approach, right? Alternatively, one can actually make some approximation of the same problem, and then you will end up showing that basically that will give you a regular polygon. So in the set of basically polygons, what's the best polygon that will maximize the area, and then you'll get the answer is a regular polygon of all same sizes. So with the constraint, you can actually figure out what should be the radius of that polygon, side of the polygon, and things like that. And then if we keep on reducing the length of the angle of each of these triangles in that polygon, and in the limit we can show that it's going to go to be a circle. So again, we'll get the same answer, there's no doubt about that, but it's not easy. I mean, with very powerful computers these days, one can actually solve this particular problem without difficulty, but it has to go through all these limits and things like that. You will never get perfect answers. But the point of doing some of this mathematics is not just about how to solve approximately, but to understand the exactness of this particular problem, and then perhaps get a technique that's much more straightforward. So here's a remark that I'm going to make. Many times we actually go into continuous spaces or continuity and things like that simply because actually it simplifies the solution, not complicates. But if you have to solve it numerically, you have to stick to discretization of the problem, which humanly impossible to solve, but computers can solve, but it will never give you exact answers. But then if there is a way to actually get exact answer in a very simple manner, then we go for that, right? So anyway, so instead of that, I am going to basically now define a continuous way of doing it. And so the area of this particular thing is going to become integral. I don't have to tell you that at this particular stage. So basically the area of any such thing is simply half r square theta d theta, right? So that's something that we know from our high school perhaps. Basically this is the area. So, and we are trying to maximize this area, okay, but subject to constraint. What's the constraint? The perimeter has to be this thing. What is the perimeter? Of course, integral of 0 to 2 pi r of theta d theta is equal to L. So there's, we have to solve this. Now, unlike the standard optimization problems we looked at it, how do we take, there we took derivative with respect to the variable of optimization, which was a vector or this thing. So we knew how to take derivatives with respect to vectors or scalars. The scalar is obviously a simple case, and then we did that, right? But here the variable of optimization is a function. So how do we take derivative with respect to function? And one can actually do an abstract way of defining derivative, and then that may be an appropriate thing to do, but we will actually stick to lot simpler approach called calculus of variations, and then we will therefore forego this particular problem for now. We will get back to this particular problem, but hopefully you understand the optimization involving functions. They will typically have these integrals. It can be maximum or something like that, so which can be converted approximately to another integral. So it will be things like that. So always approximated to some integral.